10 times a day, the Hubble Space Telescope goes blind. It reaches a patch of sky above South America and powers down its own cameras. Is that a design quirk, or is it a warning? The region is called the South Atlantic Anomaly. It is the weakest point in Earth's magnetic field, and it has been growing. 15% of the time, Hubble flies with its detectors dark. 3 camps of scientists disagree about what that means. One camp believes this is how a magnetic pole reversal starts, something that has not happened in 780,000 years. Another reads the data differently and calls the anomaly a recurring blip, one that has appeared and disappeared dozens of times in 9,000 years without triggering a flip. The third camp says both sides are wrong. The cause is not in the field. It is 3,000 kilometers below the surface, and nobody can reach it. In October 2025, the European Space Agency published 11 years of continuous satellite measurements of this region. The weak spot had expanded by an area roughly half the size of continental Europe since 2014, and around 2020, it did something the models had not fully predicted. It split into 2 zones. The South Atlantic Anomaly is measured, mapped, and monitored continuously by every space agency on the planet. It is a crack in the barrier that stands between all of us and the charged particles streaming from the sun. The evidence points 3 directions. You will have to pick a side. Start with what the anomaly does to the machines that cross it. On March 26, 2016, the Japanese Aerospace Exploration Agency lost its most advanced X-ray observatory. The satellite was called Hitomi. It had been in orbit for barely 5 weeks. The cascade that killed it began during a routine pass over the South Atlantic. A star tracking sensor failed to update the onboard navigation unit. The system detected rotation that was not actually happening and tried to correct it. That correction created real rotation. The backup thrusters fired in the wrong direction. Within hours, Hitomi was spinning so fast that the centrifugal force ripped the solar panels from the body. Ground controllers watched the telemetry collapse in real time. The satellite broke into multiple pieces. Japan's investigation found that software errors drove the cascade, but the cascade began in the one region of Earth orbit where radiation is strong enough to disrupt the sensors that satellites depend on to know which way they are pointing. Hitomi was not an isolated case. Satellites have been failing in this region for decades. The Global Star Satellite Phone Network reported losing multiple first-generation satellites in 2007, with cumulative radiation damage from repeated passes through the anomaly cited as the likely cause. The SpaceX Dragon capsule docked to the International Space Station experienced a transient computer problem during a transit in October 2012. Skylab's solar flare detector threw false alarms every time it entered the zone in the 1970s. NASA reported that standard laptop computers aboard the space shuttle crashed during passages through the anomaly. And the Pamela particle physics experiment, designed to study cosmic rays, measured levels of trapped antimatter inside the anomaly far higher than models predicted. The radiation belt was holding antiprotons directly above South America. Then there are the astronauts. Crew members aboard the ISS have reported seeing bright white flashes with their eyes closed while passing through the weak spot. Those flashes are not a psychological trick. They are caused by high-energy cosmic ray particles striking the retina with enough force to trigger a visual response. The radiation is physically hitting them in the eyeball. The ISS was built with extra shielding specifically because of this region. The station crosses the zone multiple times per day. Its orbit is inclined at 51.6 degrees, which means it cannot avoid the zone. The shielding protects the crew from the worst of the exposure, but external instruments are far more vulnerable. Brian Blair, the deputy principal investigator for the GEDI laser instrument mounted on the outside of the station, reported regular glitches and resets during passages through the anomaly, each one causing a small amount of lost data. Multiply those losses across every instrument on every satellite in low orbit, and the cumulative cost of the anomaly becomes something no space agency can ignore. The reason all of this happens in the same region comes down to one structural fact about this planet. Earth's magnetic field is not a clean, symmetrical shell. It is generated by a churning ocean of liquid iron in the outer core, roughly 3,000 kilometers below the surface. That motion creates the field that deflects most of the charged particles streaming from the sun. But the field is lopsided. The magnetic axis is tilted about 11 degrees from the rotational axis, and the center of the magnetic field is not perfectly aligned with the center of the Earth. Over that region, the field is weaker than anywhere else on the planet's surface. How weak? The inner Van Allen radiation belt, a ring of trapped high-energy particles, normally stays well above the altitude where satellites fly. But over the weak spot, the belt sags down to 200 kilometers. That is lower than the orbit of the International Space Station. Every satellite in low Earth orbit crosses this zone. There is no alternative path. Hubble passes through it 10 times per day and spends 15% of its life in the region, with its light-sensitive cameras powered down to prevent permanent damage. The most capable space telescopes humanity has ever built fly blind over one part of the planet on a fixed schedule. And the weak spot responsible is not stable. It is expanding faster than any model predicted a decade ago. The World Magnetic Model is the mathematical map used by every GPS device, military navigation system, and commercial aircraft on the planet. It is updated every 5 years. In 2019, the field was changing so fast that NOAA and the British Geological Survey had to release an emergency update a full year early. That had never happened before. The field was outrunning the model built to track it. The 2025 version introduced a 10-fold jump in resolution, from 3,300 kilometers down to 300 kilometers. That upgrade was not optional. Without it, a ship sailing from South Africa to the United Kingdom on the old model would have arrived 93 miles off course. 93 miles? Because the invisible lines guiding the compass had moved faster than the map could follow. The North Magnetic Pole has been drifting from Canada toward Siberia for decades. Its speed peaked at roughly 55 kilometers per year, then dropped to 35 kilometers per year. That deceleration was the steepest ever measured. In early 2026, the North and South magnetic poles briefly shared the same longitude, for what may have been the first time in centuries. Between 2014 and 2025, ESA's swarm satellites measured the South Atlantic Anomaly continuously from orbit. SWARM is a trio of identical satellites, launched in November 2013, designed specifically to map the magnetic field with high precision. After 11 years of unbroken data collection, producing the longest continuous space-based magnetic record ever assembled, the results were published in Physics of the Earth and Planetary Interiors. The anomaly had expanded steadily for the full 11 years. But since 2020, a second zone of intense weakening had developed southwest of Africa. The eastern zone was losing field strength 3 times faster than the original western zone centered near South America. Chris Finlay, the lead author and a professor of geomagnetism at the Technical University of Denmark, described what SWARM found happening beneath the surface. In the southern hemisphere, magnetic field lines are supposed to emerge outward from the core. But underneath the weak spot, SWARM detected patches where the field reverses direction and plunges back into the core. One of those reversed patches was drifting westward toward Africa. That drift stretched the anomaly until it fractured into 2 lobes. So if the weak spot is a wound, the question every geophysicist wants answered is whether it is healing or spreading. That is where the 3 teams split. Start with the number that started the argument. Earth's magnetic field has weakened by roughly 9% in the last 200 years. The reversal camp reads that as a countdown. Reversals have happened 183 times in 83 million years. The last one was 780,000 years ago. For this camp, the weakening field, the pole drifting towards Siberia at 55 kilometers per year, and the anomaly splitting in two all point the same direction. Something is starting. Nilsson's team at Lund University took that same 9% and ran it backward. They reconstructed 9,000 years of magnetic field behavior from burned archaeological artifacts, volcanic rock, and ocean sediment cores. What they found gutted the reversal argument. Similar anomalies had appeared and vanished repeatedly across those 9,000 years. Not one of them preceded a reversal. The field weakened, the anomaly grew, and then it recovered. Over and over. Same measurement. Opposite verdict. The reversal camp sees a system that is overdue. Nilsson's camp sees a system doing exactly what it has always done. We do not have to guess what a collapsing field does to this planet. It happened before. 42,000 years ago, it actually happened. During an event called the La Chance excursion, Earth's magnetic field dropped to roughly 25% of its current strength. The poles briefly reversed, then reversed again, and the whole episode lasted about 440 years. A kauri tree preserved in a New Zealand bog captured the chemical fingerprint of that collapse in its growth rings. Carbon-14 levels in the wood spiked because without a strong field, more cosmic rays reached the atmosphere and produced more radioactive carbon. Researchers at the University of New South Wales matched the tree ring data against geological records and found the correlation was precise. The field weakened, vanished, reversed, then flipped back. The tree captured every stage of it in the chemistry of its wood, one ring at a time. During that event, the ozone layer thinned. Ultraviolet radiation at the surface increased. Climate patterns shifted. Some researchers have linked the event to sudden changes in human behavior, including the earliest known surge in cave painting across Europe. The connection to human culture is debated. The connection to increased surface radiation is not. But here's the number the reversal camp does not like to mention. Earth's magnetic field right now is roughly twice as strong as its average over the last 1 million years. The 9% decline over 2 centuries sounds dramatic until you measure it against the full historical range. The USGS has stated directly that a reduced field does not mean a reversal is coming. The field can weaken and recover without flipping. It has done exactly that, many times. Chris Finley, the researcher who mapped the split, put it simply: reversals are chaotic. Being 780,000 years past the last one does not make the next one more likely. The core does not run on a clock. The gap between what the data says and what most people assume is the reason this investigation exists. So if the weak spot is probably not a reversal, what is driving it? The third camp has a suspect, and it has nothing to do with the field. Halfway to the center of the Earth, about 3,000 kilometers down, the rocky mantle meets the liquid iron outer core. Directly beneath southern Africa, sitting on that boundary, there is a mass of ultra-dense rock, roughly the size of a continent. Geophysicists call it the African Large, Low Shear Velocity Province. The name comes from what happens when earthquake waves pass through it. They slow down. That slowdown told researchers the material is denser and structurally different from anything around it. It has been sitting there for tens of millions of years, possibly hundreds of millions. It is one of 2 such structures on the planet. The other is beneath the Pacific. They are the largest known formations inside the Earth, and they were only discovered because earthquake waves from the far side of the planet kept arriving late. Nobody can drill to it. Nobody can sample it. Nobody has ever seen it directly. The only way to study it is to wait for an earthquake on the far side of the planet and measure how long the vibrations take to reach the other side. Every piece of evidence is indirect. But the third camp argues this formation is the single most important factor in the weakening above it. The dense mass disrupts the flow of liquid iron in the core directly overhead. That disrupted flow creates the patches Swarm detected where the field turns inward instead of outward. a localized obstruction in the river of molten iron that powers the entire field. The reversal camp pushed back. If the cause is local, a single blob beneath one region, then why is the entire global field down 9%? The third camp pointed to the swarm data. The blob is not the only reverse flux patch. There are others, smaller and harder to track, scattered across the core mantle boundary. The 9% decline may not have a single cause. It may have several, all feeding from the same turbulent layer of liquid iron. The blob is simply the largest and the most measurable. The swarm satellites that mapped the split are the same instruments that tracked the field during the May 2024 geomagnetic storm, the strongest in more than 20 years. That storm pushed visible auroras as far south as Florida. If you want to understand what the solar wind does to a field already under strain, that event connects directly to what is happening here. Which camp do you think has the strongest case? Drop it in the comments and back it up with one piece of evidence from what you have heard so far. Now take the scenario where the field does keep weakening toward Lasham's levels. Not tomorrow, not next year, but steadily, decade after decade, the way it has been trending since the first magnetic measurements were taken in the 1830s. What would that actually do? 183 magnetic reversals in 83 million years. Every single one of them, life on this planet survived. There is no mass extinction in the geological record that lines up with any known reversal, and the USGS has confirmed this directly. Reversals happen, and biology continues. But biology 83 million years ago did not depend on GPS constellations. It did not depend on power grids, undersea fiber optic cables, low-orbit communication satellites, or the International Space Station. The magnetic field does not need to vanish for those systems to fail. It only needs to weaken enough for a sufficiently strong solar storm to reach them. During the May 2024 storm, the field was at full strength. The storm still disrupted satellite operations and pushed visible auroras to latitudes where they had not been seen in decades. Run that same storm through a field at 25% strength, the level Earth experienced during the La Champs event, and every satellite in low orbit faces elevated radiation exposure. Power transformers connected to long transmission lines become vulnerable to induced currents. And navigation systems that depend on magnetic models lose accuracy at exactly the moment you need them most. The damage would not arrive as a single catastrophic event. It would accumulate quietly over months and years of reduced shielding, compounding with every storm the sun sends our way. The cascade matters more than the initial hit. A degraded GPS constellation means emergency services lose positioning, accuracy. Weakened satellite communications mean financial transactions slow down. Damaged weather satellites mean forecast models lose data inputs, which means storm warnings arrive late, which means shipping routes become riskier, which means insurance premiums climb, which means the cost of everything that travels by sea goes up. The magnetic field is invisible. The economy it protects is not. If you know someone who works in aviation, shipping, or military navigation, send them this video. If you know someone who saw the 2024 auroras and thought it was just a pretty light show, send it to them too. The field they depend on is the field this investigation is about. Mars is the bluntest warning about what happens when a planet loses its magnetic field entirely. It once had a global field, generated by a core that was hot enough to churn. When that field collapsed, the solar wind stripped away most of the atmosphere over hundreds of millions of years. The surface went from potentially habitable to radiation blasted and barren. Earth is nowhere close to that outcome. The field would need to disappear entirely and remain gone for geological ages. But Mars proves that the shield is not optional. Without it, the atmosphere thins, the surface changes, and the planet becomes a different kind of place. The 2025 State of the Geomagnetic Field Report, published by NOAA in January 2026, confirmed that the weak spot expanded by 8% in a single year. The field intensity at the center of the anomaly dropped by roughly 30 nanotesla at the surface. The anomaly continues drifting northwest. The strong field region over Canada is shrinking by roughly the area of India. The strong field region over Siberia is growing by roughly the area of Greenland. The geometry of the shield is changing in ways that are measurable from one year to the next. A geomagnetic jerk, a sudden shift in the rate of field acceleration, was detected between late 2023 and early 2024. Jerks have happened before. They are often followed by altered drift patterns and shifts in regional field behavior. The fact that one occurred so close to the release of the New World Magnetic Model means the model's predictions may diverge from reality faster than expected. None of this means a reversal is coming. The scientific consensus, stated by both the USGS and ESA, is that a weakening field does not reliably predict a flip. A 2023 study in Geophysical Research Letters found that reversals can only be detected once they are already underway. There is no early warning system for a magnetic reversal. The models that track the field are updated on a 5-year cycle, but the field itself does not wait for the next scheduled release. It sometimes changes faster than the models can follow. The 2019 emergency update proved that, and the 2023 geomagnetic jerk confirmed it all over again. Every prediction carries a built-in expiration date, and the core does not wait for the next scheduled update. The field is monitored by the same satellites it threatens. The instruments watching the crack are the ones most at risk from it. Swarm has been operating for over 12 years, far past its planned mission lifetime. When those satellites eventually fail, the continuous record they provide will have a gap. And gaps in the data mean gaps in the ability to predict what the anomaly does next. 3 camps, 3 readings of the same evidence. The reversal camp points to the weakening, the drift, and the split, and sees the early chapters of a process that takes centuries to complete. The recurring blip camp points to 9,000 years of data and sees a familiar pattern that will resolve without a flip. The core dynamics camp points 3,000 kilometers below the surface and sees a localized disruption driven by a structure older than the human species. One question cuts through all of it. Is the weak spot getting worse, or is it doing exactly what it has always done? That is the only verdict that matters. Put yours in the comments. And if this investigation changed how you think about the ground beneath your feet, hit the like button. The South Atlantic Anomaly is not visible from the ground. You cannot feel it. No instrument in your house will register it. But 15% of the time, the most powerful telescope in orbit crosses it blind. Twice a day, the ISS passes through it. Every low-orbit satellite follows a fixed path through the weakest point in the planet's shield. That weak point is expanding, splitting, and deepening by the year. And the only tools capable of tracking what happens next are the same machines. The anomaly is slowly degrading. The next abyssal cosmos investigation goes deeper, a force so extreme it bends light, crushes atoms, and rewrites the rules of physics in a fraction of a second. If what you just watched is a crack in the shield, the next case is what happens when that same force has no limits at all. Subscribe so you do not miss it. The next case file is already being built.